Hello, everyone, and welcome to episode number 94. We're going to be exploring a new type of cluster API implementation, a new implementation of a virtualizer today. I think it'll be really fun, but we're going to kind of dig into like what it takes to make everything work, and we're going to do sort of a different exploration of things than we have in the past. So it should be fun. Let's check it out. Let me share my screen here. Share screen, entire screen. There we go. All right. Our notes, as always, are available at hackmd.io/@echo-live, and you'll be able to find episode number 94 there and be able to see those notes. If you're out there in the chat, do let me know. It's lovely to see folks joining me on an episode like this. It's always great to know that folks are out there. So today we're going to explore a bit about a new cluster API provider. And before we do that, we're going to kind of build our way up to it. So this will be kind of an interesting one. First, let's get into some of the news and the highlights and stuff that have happened this week. And then we're going to talk a little bit about the events that are coming up. And then we're going to jump into kind of the fun part of the episode here. So our newsletter this week is from May 31st or May 30th. And gets into some of the more recent work. Like I think they mentioned this last week on eCHO, but BPF Comp recently wrapped up. And if you weren't invited, then you can still catch up on the slides, like Alexei's talk. What should be the anthem of BPF, and what are where in the trough of disillusionment are we with a verifier, etc. Lots of really good stuff, including unit tests for eBPF programs, eBPF Dev-Explorer. Hey. Welcome. Glad to see you, Max. Hey, Jamie. Good to see you. I think you're gonna enjoy this one. This is actually pretty interesting. Stuff that's happening in the ecosystem. Cilium Mesh is a new way to extend Kubernetes benefits across on-premise and cloud networking. And this one is a really interesting one. The name of Cilium Mesh is a little tricky. I'll admit that, but basically the write-up actually does a pretty good job of explaining what it is. So Cilium Mesh, in some ways, is very comparable to like to a gateway model, wherein you can actually put another device in your network that would allow you to identify and observe traffic as it enters into a cluster. And that's pretty neat stuff. So lots of really good stuff happening in that space. The how-to introduction to Cilium. There is now a Linux Foundation intro course, which is pretty neat stuff. It's going to start on June 9th. If you're interested in taking the LF certification for Cilium, that will now be available. There's a using Cilium for Kubernetes networking and observability. Learn how to install them, of course, and then Cilium installation tips. Use Helm chart and IPAM configuration, load balancer, and tunnel mode. A tutorial on how to deploy Cilium on top of AKS, including the ability to actually spin up an AKS cluster and use Cilium as a Cilium Enterprise directly in your AKS cluster, handling upgrades and all of that stuff automatically for you. Very cool stuff. There is a Cilium workshop with Isovalent and Superorbital, or Orbital, not Orbitable. Other stuff is the next one coming up is actually the next event, which I'll be hosting in San Francisco at the Mina Gallery, which was right around the corner from where CoreOS was. I spent quite a bit of time at the Mina Gallery. Mr. Josh Rosso. Hello, good to see you. So at the Mina, and we got Tony Norland. Welcome. Glad that you're here. So at the Minnow Gallery on June 15th, I'm going to be hosting a Cilium and eBPF roundtable. So in this discussion, my goals are to kind of start off with like a little bit of an introduction of Cilium, like what it does, what it's good for, kind of welcome the new folks in the community kind of around that. This is primarily like a community type event. And then we're going to get into a roundtable discussion talking about like what trends we're seeing in the space, like where do we see eBPF filling gaps and like those sorts of things. So if you have something to share or if you want to come be a part of it, definitely come join us at the Minute Gallery on June 15th. You can get to that link from the newsletter, or you can also just go to isovalent/events, isovalent.com/events, and you'll find the link to it. So come join me on June 15th if you're in San Francisco. It'd be lovely to see all of you. What else do we have in the news? There was a new recent blog, which I thought was really well put together. Zero Trust Security with Cilium and eBPF. It basically kind of digs into a little bit more of the detail about how we're thinking about solving some of the zero trust cases with MTLS and other tools with Cilium and the surrounding tooling. So definitely check that one out. I think it really gets into a lot of really great detail about how all of these things are handled and how we're thinking about it. So I'm not going to spend a bunch of time on it. It's a great article. I highly recommend you give it a read. There is a new tutorial on isovalent.com/labs. And this lab kind of digs into cross namespace routing with Cilium Gateway API. So leveraging the Gateway API to handle cross namespace routing. Pretty neat stuff. So if you're exploring Gateway API, if you don't know much about it and you want to kind of play with it a bit, this is a great way to kind of get your hands on it and play with it. All right, now for the fun part. Recently, I have heard of a new hypervisor. It's called Cloud Hypervisor. And it is a really interesting hypervisor to me because I'm always looking for ways to kind of more efficiently run virtual machines. And I thought, I wonder what the Cloud Hypervisor is. It's a it's a VMM virtual machine monitor written in Rust that focuses on running modern cloud workloads with minimal hardware emulation, which sounds pretty neat. But basically what this is going to allow us to do is kind of create virtual machines. And I thought, I wonder if somebody's actually written an implementation for this in Kubernetes. And that's when I found Vertink. Written by the SmartWorks folks. Now, Vertink is basically, all of the cloud hypervisor stuff on Kubernetes as an add-on. And so kind of comparing and contrasting the most recent cluster API implementation that I explored, they've written up a thing that kind of describes the differences between KubeVirt and Vertink. So KubeVirt leverages QEMU and KVM. It leverages libvirt. And in so doing, it creates like a full virtualized machine, whereas Vertink actually lowers it a bit, right? It means that the actual memory utilization of a virtual machine can be a bit smaller, and it can be a bit higher performance, and it has a bit of a smaller attack surface. It does not require a long per pod launcher process, which further reduces the runtime overhead, memory overhead by about 80 megabytes, which is kind of impressive on a per machine basis. It is an especially good fit for running fully isolated Kubernetes clusters in an existing cluster. So they actually have a couple of different things here. One is a cluster API provider for Vertink, and the other one is a tool called KNest, which kind of digs into it a bit. So I thought, you know what, let's just explore this. Let's play with what's out there. So the first thing I did was I went ahead and created, I went through this kind of tutorial. And I really like how simple this is to install. So I thought, let's give it a swing and try it out. So let's kind of go back through what happened here. So I did create cluster. Oh, shoot. That's not going to work, because the other thing they tell you, well, actually, it probably should work fine, but let's do this. Delete cluster name equals Vertink. What this is going to do is create a single node kind cluster with no CNI installed. And the reason I'm starting with the hypervisor first is because I want to know that the hypervisor itself is going to work before I kind of jump into exploring what's going to happen with cluster API. And I also want to take a look at the VM that it creates. I want to understand, like, can the VM do stuff? Is it going to work for me? Is it going to work for our environment, et cetera, et cetera? So let's kind of dig into that a little bit. So this doesn't have a CNI installed, so let's go ahead and install one. This will just install Cilium in kind of a default mode for kind. And then the next thing they ask is that we install a version of Cert Manager. So we even have a little line to do that. Let's go ahead and do that one. Hope you can all hear me okay. Otherwise, I think somebody probably would have said something by now, but I did have problems with my audio last week. So the container runtime is containerd. We're good there. Hardware virtualization, we definitely have KVM on this box. Minimum version way above it. So let's go ahead and install Vertic. Now this gives me Kernel. Get paused. Everything's pretty much up and running. Sweet. Okay, let's go ahead and grab this example. Oop. Copy. Now, I was pretty curious about this one because what's happening here, let's take a look at this pod. Let's take a look at this YAML real quick because I think it's pretty neat. What's going to happen here is it's actually copying in the Vertic container root fs Ubuntu, which is basically just a cloud image for Ubuntu. And then it actually, they make their own kernel, a version of the kernel at 5.15.12. We're going to dig into this a little bit more, but this is basically the image for the kernel, and then the command line being passed into the kernel is console tty s0 and root of dev vda, and it's making the root partition read write. But the really interesting bit is down underneath the root file system, there is also a cloud.init, where basically it's saying, you know what, we need to have some access to this thing. So what we're going to do is we're going to actually enable password auth for SSH, and we're going to give it just a dumb password. And we're not going to allow that password to expire. So this is really just kind of like hacked together in a way that would actually make it so that we can jump into this node. So if I do kubectl get pods, I can see that it's running. And if I do kubectl get virtual machines, I can see the virtual machine has been created. And if I do pgrep cloud -a, I can see this is the process that's running this virtual machine for me, right? And I'm using that Rust binary cloud hypervisor. It's giving it an API socket. It's giving it a console. That's where the kernel is located. Console TTYS0, CPUs, boot one, got a whole topology set up, memory. There's the disk. And then there's the cloud.init that's been created. And then there's the MAC address that's been generated for it, and it's been given a tap device in the E0, or a tap device of E0 inside of the thing. So that's pretty neat. It actually started the whole thing up. And if I do, say, bpytop, let's just take a look at how much memory this thing is just using it at idle state. Here's the other guy. It's the kubelet. So it's using 190 meg of memory currently. Kind of neat. So that is a running VM. So it seems like things are working, but with Cilium and some of the more advanced feature sets of Cilium, as we continue to develop it, we want a node that is going to have BTF data. And you can tell if the Linux kernel that we're running has BTF data by looking at sys kernel BTF. And if you see, typically I'm looking for VM Linux. But if this file exists under the sys file system, what that means is that the VM Linux, the BTF data for the kernel itself has been shipped with the Linux kernel. It's actually packaged up and shipped as part of your Linux kernel that you boot into. And it's an important one for a lot of the kind of the more recent and interesting developments for Cilium and all of the other interesting parts of the data path, like everything that we're writing for eBPF programs and stuff. And the reason it's important is that the way that eBPF kind of effectively functions is it gives you the ability to kind of intercept and observe and make changes to system calls or different inspection points within the Linux kernel pretty much across the board. Everything from file system to networking to sockets, like everything that could happen, everything that you could basically interact with on the kernel layer, you can write an eBPF program for inspecting it or manipulating it or doing things like that for any part of those calls. But when you do make that interaction with the Linux kernel, if you think about it like an API, you're basically making these system calls and they look like just integers, right? So like a call that says file open, when it shows up through that API, will just have an integer. And we need some way to map that back to a function call so that we understand like what structs are expected and all of that good stuff as part of that as part of that API call. The way that we do that mapping is BTF data. In a lot of ways, it's kind of very similar to like having the debug info for a binary, right? So if you had like a Go binary or some other or some other like C type binary, and you wanted to use GDB to interact with that binary and understand where your application is hanging up, and like understand the different functions that are being used and those sorts of things, you would need a debug. But you need debug symbols to understand like how to map those function calls to something that are easier for you to understand and parse. And so these are kind of like debug symbols for the Linux kernel and for any other module that you have deployed within your Linux kernel. And the other thing that's interesting is that it actually also, and so we need those things to be able to write an eBPF program that will be portable. So for example, when I'm going to write an eBPF program that will inspect something happening at, I don't know, the socket layer, for me to make that a portable eBPF program, that mapping is really important, and it needs to be relevant to the kernel that is running. And so the way that I maintain that relevance, the way I make eBPF programs portable, is by including BTF data in every kernel where I want that eBPF program to run. This is an effort, a pretty wide-ranging effort within the Linux kernel community that enables, that is called core, or compile once, run everywhere. And the core effort is the intention, is the work of making it so that BTF data is available in every modern Linux distribution and changing the way that those kernels are compiled to be able to support the building of BTF data so that every Ubuntu, Red Hat, whatever kind of kernel it is, will actually have that data. Now that was a big info dump, but it all comes down to the fact that like I want to be able to see syskernel BTF VM Linux when I go into this running VM. Let's take a look and see what's possible. So I'm going to do a kubectl run it bash image equals bash bash. Disconnect real quick, reconnect. I'm going to install the OpenSSH client, apk update. OpenSSH client. And then I'm going to do, let's see, // Ubuntu at, I forgot to do kubectl get pod -o wide. So the running VM Ubuntu container root fs has the IP 10.244.0.2.11. Yes, and the password is, of course, password. And so long since I logged into a box with a password that it's like kind of mind-blowing to me. So here is our uname-a. We can see that it's Linux 5.15.12. And if I had to take a look at cat sys kernel, no BTF data. This one was built without it. All right. So I want to change that. I want to make it so this kernel, when being compiled, does include BTF data. So let's take a look at how this kernel is being generated. Image builder. But to do that, I kind of went and looked at the kernel that was going to be used by the cluster API for VertInc. And they have a copy of a project called Image Builder. And this is how they're going about building these images, which is pretty neat stuff, right? So the kernel, the Docker file, and you can see that they're using Fedora to do the kernel build. It really doesn't matter what you use to do the kernel build. It just matters that it has all of the necessary pieces to actually include the BTF data. And this one does not. There are a couple of different pieces that are currently missing in this setup. And we're going to walk through it and try to get it working. So let's go ahead and fix this up. What I'm going to do is I'm going to extend this configuration to be able to support config debug info. See, this right here is the problem. Config debug info is not set. So I want that to be set, and I also want it to include config debug info BTF, which will basically mean that if you have all of the necessary prerequisites, it will actually compile into this Linux kernel at compile time all of the BTF symbols that we need. So let's go ahead and try this out. So let's kind of take you on that journey a little bit. It'll be kind of a fun one. I hope this is interesting to y'all. This is kind of some interesting Linuxy type stuff, but this is kind of where I was at when trying to explore this kind of stuff. And I thought, it might be useful to you if you have ever run across this. But let's play with how this actually works. So what I did was I pulled the Capch image builder down, and I went ahead and I edited the file. And the first thing I did was I added this piece right up here at the top. So dwarves is actually a prerequisite for compile time for the Linux kernel that includes PA hole and a bunch of other stuff that basically allows you to parse all of that BTF data and compile it into the Linux kernel. If you don't have PA hole in the file system, it won't actually, and all of the necessary libraries, it won't be able to, even if you were to set the kernel config correctly, it wouldn't be able to compile a Linux kernel that has all of that BTF data encapsulated within it. So I added this piece, adding the dwarves package to the initial install. And then I saw that they were copying Linux config x86-64 in. So let's go ahead and do that. Same thing. Kernel, and Linux config x86-64. And the next thing I did was I went ahead and enabled debug info equals y. And then I also had to add a few other pieces, right? I had to add the toolchain default. Just go ahead and use the dwarf toolchain default. And then I had to add info BTF. And I didn't have to do this. I went ahead and added the BTF modules. And that's why you don't just see the VM Linux, you also see the BTF modules for all of the other modules that are being installed. It was kind of a bunch of work. It took me about an hour this morning to get this all figured out. But I kind of wanted to take you on a different little journey here real quick, because I thought this was pretty interesting. And this is how I went about actually making this work. So I did Docker run. What I'm going to do is I'm going to copy the local the Linux config in here, and I'm going to run some of these commands by hand, because what I was trying to understand was like how to actually build this config. So if we take a look at how the Docker file is building it, what I've done here is I've gone ahead and started a Fedora 35 container. I'm going to go ahead and set my kernel version correctly. And then I'm going to do just each step to kind of work through and build this kernel, because what I really want to do is make sure that the step that is actually doing this right before this make happens, I want to do a make old config and show you how I came about the flags that I set. So let's go ahead and do that real quick. So export kernel version equals horizontally file. Kernel version that they were using was 5.5.12. And then the next thing we do, grab all this stuff. You know, I missed dwarves, which we'll put in there in a second. All downloaded here. All right, so install all the things. You can see that our current install does not have pholes, so we're going to do yum install vim and dwarves. Now I do have phole. Yep. And I have vim. Okay, so the next thing we want to do is continue on with the steps. So we do a git clone of a branch of the Linux, a Linux branch that the Linux Cloud Hypervisor is using. This is one of my favorite parts of this. Depth 1 makes it super fast. Ooh. Let's try this again. Hitting a bad mirror somewhere. That's better. Okay. So what was happening there was when we were looking at the data transfer rate, it was actually very small. This was like going to take forever to download. This is now like 400K. I can get megabytes a second, but sometimes I get like a bad mirror and it takes forever to actually download. But hopefully this won't take forever. This is already at 10%, and then we'll be able to actually go through the next steps here. So to recap, what we've done so far is we were kind of like exploring a new hypervisor that's called Cloud Hypervisor. The Cloud Hypervisor basically enables me to use like a single Rust binary that will handle all of the emulation necessary to spin up a new VM. And for my purposes, I tried to make it work in Kubernetes. We were able to do that. We were able to deploy virtinc into a cluster, a kind cluster, and then we were able to actually deploy our first VM. And that's when we noticed that the VM kernel didn't have BTF data. And so we're kind of working through the steps to make sure that the Linux kernel that we're going to deploy when we get to the Kubernetes part of this is actually going to include BTF data. So to do that, we have to enable some flags in the Linux kernel config, and then we're going to rebuild our kernel. We'll push it up to our repository, and we'll try it again and see if our BTF data is present in the newly built Linux kernel. That's where we're at. We're about 32% on the download. If I was smarter, I probably would have just copied it in. Let's see what happens if I try to pull it locally. Oh, export. Yes, yes. Yep. Ah, see, that's much faster. That's so fast, in fact. So I'm going to do it this way instead. All right. Here is setup. We're going to do the next part we're going to do here is go back to our notes. We're going to go ahead and do our install of this again. That will still be faster. You see dwarves and Vim. All right. So what happens next here is once we get this actually downloaded, we already have it downloaded in our case. So the next thing we're going to do is instead of actually doing our make command here, which is make BZ image, and then tries to produce it with as many CPUs as it has available, what we're going to do instead is we're going to do make old config once this step is done. And then we're going to make sure that our new config actually has all the things necessary to compile BTF data into our Linux kernel. And that will be kind of the interesting part of that. And then I'll show how that actually how I'm updating that for the image that I'm hosting, and then we'll try it out. All right. So if you ask somebody who tells you, if you want to build a Linux kernel that has BTF data, people will tell you just to turn on the flag for the non-info piece. So let's just actually look at this real quick. CP Linux config 64, and we're going to copy that into .config. I'm going to edit that .config, config info, config debug. Now, before, next, config debug info. Set to no. So I'm going to set it to no. I'm going to delete these things. So with set to no, it was just not set to anything. So it would look like this. Yeah, exactly. So that would look like this before, right? Config debug info is not set. Now, if you see a Linux kernel config that looks like this and you want to enable the BTF data, then what you need to do is actually turn on that whole section in the config. Right? So we could do config debug info equals yes. And this turns on a whole new section in the Linux kernel config. And if I do make old config, then it will go about trying to do, it'll take a look at that old config and it will see, that I can't type, and then I'll correct my horrible mistake. YYP config debug info is a yes. And I'll do make old config. And it will say, hey, you've turned on a new section. Here are some questions related to that section. Do you want me to reduce the amount of information? I will say, I'll just go with the defaults for a lot of this stuff. Do you want me to split the things? I do want to rely on the default tool chain. Do I want to include debug info BTF? And I'm going to say yes. Now, if I take a look at that vim config, I can see that BTF data is set to yes. I can see that a BTF modules is set to yes, and I can see the dwarf toolchain is set to yes. And I just kind of went with the defaults after enabling config debug info. So in theory, that should be the new config that I need, right? So let's take a look at that config again. Let's actually copy this config to the Linux config 64. I'll exit. Now if we do ls-al, we can see that the Linux config rep df Linux config 64. We can see now that that data is present. So now this configuration will enable the encapsulation of BTF data in that Linux kernel. So let's try and build that. Let's go back to the make file, which is here. And we will do make, and then let's just take a look at the make file. And what I did first when I was actually digging through this was I went ahead and changed the repository to my own repository, Maui Lion. And then I also changed a couple of the things that were kind of making me nuts. Like before, they were using a dash here instead of a colon. So that meant that they would generate a new repository for every kernel version and that the only image tag would be latest. And that seemed odd. So I just kind of reconfigured that to use colons, which is a good thing in my mind. And then it went ahead, and then I went through and did a couple other things here. Including I moved the platform section up and I changed it to just include Linux AMD 64 for now. And I commented out the ARM 64 build because this is really This is an AMD 64. This is an AMD 64 box. This is an x86 box, and I really only care about that image. And so, for my purposes, I just wanted to build the AMD 64 platform. So now, in theory, we should be able to do make push kernel, and it will go through the steps. And since I did actually just recently build this, it's already got the checkout of the source repository, so that's all good. And this is basically just building against that new config that we generated. And it will push that new kernel up, and then we'll try that new kernel in our pod YAML and see if it's different. And if it is, we will proceed to exploring the cluster API piece. Ooh, cooking that CPU, building that thing with all the CPU. Oh, even my camera's a little slower. Ooh, nice. Building a Linux kernel live on screen. While we're waiting for this to build, let's go back and read a little bit more about Cloud Hypervisor, because for my purposes, what I care about is that it's just a single binary that runs all the emulation stuff, which is mind-blowing to me. So this is actually a project that's working from Alibaba, AMD, Ampere, ARM, ByteDance, Intel, Microsoft, and Tencent Cloud. And it's a really cool project. It's making pretty fast progress for a new hypervisor. And the way that it actually does its thing is like kind of mind-blowing. Like the amount of CPU that it's the fact that it's able to like reduce the amount of resources necessary to produce this stuff is pretty wild. And as you can see in the build place, or in the build configuration, you could actually spin up an ARM 64 image or an x86 image. In my case, I'm really only, in this particular demonstration, I'm only caring about the x86 image, but there's nothing keeping me from deploying an ARM image here because it's still just virtualization. Pretty cool stuff. Still building. We're nearly there. There's probably a bunch more of this that we could actually cut out, but I'm not going to really work on optimizing the Linux kernel for a demonstration like this. I'm just going to go with whatever they have configured and add in the bits about it, BTF. All right. Wonder how to whole guest agent thing. Like, yeah, it's true. It's a good question. I'm actually curious about that myself. But it is pretty neat that they have, like, in their VM scenario, a way to actually spin up or make use of, like, this is the thing that kind of tripped me out, Josh. I was pretty impressed by this. So the pod YAML includes the ability to just enumerate cloud user data right directly into effectively just a volume that is including this data, which which opens up a whole new world of just being able to spin up like virtual machines that are configured in a way that you care about, pretty wildly, right? Like, because at that point, once you have cloud config and you could just spin this stuff up kind of automatically, that's a pretty wild set of tools just by itself, right? Like a gig of memory, and like you can configure how much space the thing's going to get. Pretty impressive stuff. And if I do kubectl, let's say describe, this is the virtual machine that was created. It's got one core, one socket. That's the MAC address, kernel command line. Yeah, 4 gig of file system. Pretty cool stuff. Hey, we're almost done. We're just finishing this up. Saw some BTF stuff go by, and we are finished. And pushing. Okay, so now I've got that new image that I just built, which is this Maui lion capch 51512. We'll just copy that. We'll edit our pod YAML. Grab that image here. And one thing I noticed, which I thought was kind of interesting, was I created a pod YAML, but then when I do kubectl get VM, VM still defined. It says failed, but it's still present. I'll delete VM, and then there are none. So there's some cleanup step where the two of them are connected, like probably like a ownership resources, where the finalizer is not actually wiping out the VM. It's just deleting the pod that created that virtual machine. So that's kind of interesting. So then let's take a look at the pod YAML. So here is our new kernel that we just built. Everything else is the same. Do we have BTF data? Applied SF, pod YAML. Get pods dash o wide. Do our pre-steps. Oh, and the VM is running. All right, that was quick. 10.244.0177. Kernel exec ti dash n bash. Yes. Password. Cat. ls. Sys. Kernel. BTF. There it is. Our symbols are present on this file system. So that means that this kernel is a kernel that I want to use kind of going forward as we go through this exploration. So this is going to give me the BTF data that I need for this built Linux kernel, which means that Cilium and all of the other tools will actually just be able to explore it or find it and make use of it. All right, next step. We're going to go ahead and work through the cluster API piece. So the next step we're going to do is we're going to go to cluster API. See, let's go ahead and look at the cluster API provider Vertic. This is the host. This is the docs that SmartXWorks are providing for managing the cluster API provider Vertic. And this one will give us the ability it kind of takes us through a little bit of a tutorial, including and this is actually also documented a bit on the actual cluster API website. So if we go to cluster API sigs.ks.io and we do the quick start, we can see the that they have actually included in here Vertic. There's now a cluster API provider and documentation for the cluster API provider Vertic. But it's a combination of the two that I think is a key for success. So for cluster kettles prior to version 1.2.1, you'll need to add this provider configuration. Let's take a look at how I have what version of cluster API for cluster kettle version isn't tagged there. So I'm using 1.4.3, so I'm fine there. And then they have a bunch of the environment variables that they care about. And then the other interesting thing is this piece here at the top that says an external Vertic cluster is recommended for infrastructure. Further details can be found in the external cluster documentation. For an internal Vertic cluster, use cluster kettle generate cluster infrastructure Vertic flavor internal CAPI quick start to generate the workload cluster configuration. So effectively, we have an external cluster because we have that one that I just spun up and made available the Vertic capabilities. So let's go ahead and work our way through that process. So over here, I want to make sure I do this piece. So let's spin up our management cluster. Find create cluster name equals CAPI config create another single node here. Cilium install. Now, what they are looking for all right, so come back over here. Okay, good. We'll do. I'm going to use the external Vertic cluster that we've already created. So it says the external Vertic infrastructure cluster indicates cluster API management Vertic components are deployed into different Kubernetes clusters, which is a recommended mode. So we'll go for it before starting the quick start guide, before launching a cluster on Vertic. the following requirements should be met. There should be a secret in the management cluster that contains the kubeconfig of the Vertink cluster, which will be used by the cluster API to access the Vertink cluster. The administrator of the kubeconfig can be used for testing, but RBAC is recommended, so we will go ahead and apply the RBAC. What this is doing is it's creating a cluster role called Vertink Infrastructure Cluster. It's giving access to virtual machines, create, delete, and get. It's giving access to services, create, delete, and get. It's a cluster role. There's a service account being created called for infra cluster. And it's been created in the default namespace. And then if you're going to launch a Kubernetes cluster on Vertink with persistent storage, which we're not going to worry about, there will be a little bit more to add to it. Okay. Kubernetes control plane controller in the management cluster will check nested Kubernetes cluster state by control plane service. A load balancer control plane service is required in external Vertink cluster, and its external IP address should be reachable in the management cluster. Set the environment variable before generating the workload cluster. Okay, so we want to deploy. We want to deploy something that will create load balancer IPs in the Vertink cluster. I don't agree with the metal LB suggestion. I'm going to go with KubeVirt here. So let's do KubeVirt. KubeVirt, sorry. Actually, you know what? I've already written this up somewhere. Yes. So this is going to apply the RBAC necessary. Let's do K CPX Vertink. Apply the RBAC. We will apply the KubeVirt Cloud Controller. We will create a config map. Nodes -o wide. We're in the 172.18 space. So I'll create map. 200.10 dash 118. So that will create create. Big map. And it will mean that and what I'm doing here is I'm actually grabbing some IP addresses from like the bottom of this 172.18.00/16 network that will probably never be used by Docker. And this will give me a range that can be reached from within my cluster, within either cluster, because they're both kind of on that same network, right? And so this configures kubebip to hand out these IP addresses and then make them available leveraging ARP inside of that same network. And that way I can actually create these things. Soon in Cilium, that will be available kind of automatically. We won't actually need to use the kubebip piece for this. But for now, that is a thing that we're going to be doing just to make it simple. Cat EOF. Apply -F. This is an interesting command because basically it's saying everything between this next enter and the characters EOF at the beginning of the line will just be applied. Will be the YAML that I want to apply. So let's go ahead and copy that all the way down to there, paste it, enter. Look at pods-AW. So now we have kubebip setting up. And kubebip is running. Okay. Now if I do kubectl create service type test and deployment. Load balancer. Get C for all. And it works. Okay, so now we have our load balancers. We're able to create load balancers. We're able to test those load balancers. Everything's working there. So we'll go ahead and do delete. PC go deploy echo. All right. Everything's good here. Now the next thing we're going to do is go through that external cluster setup here. Now we've got our load balancer set up. We've already done that RBAC piece. The next thing it wants us to do is prepare an administrator kube config of the verting cluster named verting cluster kube config. Oh, weird. I think they're really going about this in a really interesting way. I'm going to go about it in a slightly different way. Let's see. I've got this and just kind of does what they're doing. So let's take a look at that thing real quick. Functions. Big. This is the function that I'm going to use. And it's going to do a similar thing, but it's actually going to be a little simpler. And what this is going to do is it's going to take the service account that's been generated and then just generate a kubeconfig from that service account instead of going through all this work of like removing the administrative stuff. We're just going to use this scenario, which should make it simpler. And you know what I'll do is I'll just copy this whole function into the yank. I'll copy it in the notes that way. If you're curious about this function, this is not a function that I wrote, the function I found, and I've used it quite a bit since then. Let's keep going with our day here. So I have to get to an appointment here in about an hour and a half. So let's keep going. So I'm going to go ahead. That's my keyboard moved on me. And then I'm going to do create. Well, hold on. I don't think I actually created the service account yet. So I think there was a step here. No, maybe I did. Yeah, there we go. 14. So let's just make sure it's there. Service accounts. Did something. Not apply this. Cool. Create big. Oh, that's right. Yes, I had forgotten about this. They stopped creating service account tokens by default, which is a good thing. It's a very good thing. All right, so then I have to do if you want to obtain an API token. Oh, I should actually show you this. So if you run into this problem, hopefully you will not, but if you do, it'll create this account. account token is a way of making it work the way that it used to work. Is arguably less less secure, but in this particular case, I'm just trying to get this thing to work from the outside cluster. So I'm going to generate a token for this. And so what this does, if you want to obtain an API token for a service account, you can create a new secret with the special annotation kubernetes.io service account name, and it will generate the secret for you. So let's go ahead and copy this. Our service account token name is for something. For Tink Infra Cluster. Apply -f YAML. And then we do create kubeconfig for Tink secret for Tink into a cluster. But it does. Build robot secret. Did I mess it up? Tink. Apply. Token. I have a service account token. I'm going to have to fix that, but that's probably just in my script. So let's go ahead and go back through the steps that they had documented, because that will probably work. Have it. So yeah. It's because the secret's name is probably not associated with it anymore. All right. So what we want to do is, let's do this. Let's do kind get kubeconfig name equals Tink. That will do is create this scenario. Then we will go through the next steps. We want to unset the client certificate and the client key, and we want to put in this guy. So let's go ahead and do that. Already, that's that part. ditch that, ditch that, and ditch that. And then our token. Set. Copy that in here. Oh, my bad. So, oh, all right. More edit. We're almost there. Boop, 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 boop. All right. So now we have kind vertink. It's all there. It's all working. Should do fine. kubectl get pods dash a big kubeconfig. Right for the IP. Sweet. All right. I'll say. Good. Auth and I list as system service account default vertink infra cluster machines create delete get. Get virtual machines config and kubefig. Cannot list resource virtual machines in the vertink smartx at cluster scope. We have a cluster role. Have that permission. Virtual machines. Get. What the heck is going on? Can I auth? Can I am system service account? But why don't you let me do it then? If you say I can, how come I not? How come I cannot? Get yes. Oh, I see. I didn't realize it was namespaced. I'm stumped. Not totally stumped, but working on it. Speaking of secrets on the stream, I know. I'm crazy like that. Right? I did, and it still fails. This is a cluster rule, which means it applies cluster-wide. It's looking at vertink smartx.com. It's looking for virtual machines. It's allowing Git. Thank you. And Git cluster role binding. That is pointing at the vertink service account in the default namespace, and it's applying the cluster role vertink infra cluster. And it is a cluster role binding, not a role binding. Get virtual machines. That's the problem. Check that out. Virtual machines, vertink smartx.com. And then if I look at the vertink, no, that's right. API group is vertink. And the resources are virtual machines. Virtual machines. FA. Trying to get this permission to work so that we can move on with our lives here. Almost there. Bam. Cannot get virtual machines in API, but the permission is there. Missing something super obvious. This is a permissions issue that I have no more time to chase. And so we're going to move on with our lives. Kubectl. Get. Big. You. Yeah, I mean, Oh, no, because get is list. It's a good question, though, Max. And according to the auth test, I can do it. It's just not letting me. So there's something super obvious I'm missing, but I just have no more time for it. So we're going to move on. Tink cube config. Cube config. So 18 02 643. I'll get VM config. Moving on with my life. So we have that. Now let's go ahead and apply it. KCTX and copy. So there is the cube config. Now that should continue to let us move forward. I'll figure out that permissions thing another time, but I'm definitely not going to spend any more time on it today. Now the next step for us is the cluster API provider piece. We've done this bit. We've got our load balancer stuff in. We have created the secret and secret name. All right, and then we can go to our cluster API docs. Quick start for Tink. I think we've already got our provider stood up, right? Kettle, get NS. We did not. Cluster kettle. It. Infrastructure. Working. Let this get created here. Yeah, so the interesting thing about RBAC and kube is if you have get, you have list. But I don't get why that didn't work. Okay. On this bit, we've done that bit. And then we want to change our kernel, right? So everything else looks fine here. We can use your file system, but they don't have. We want to change this kernel. And the way that we do that is through another environment variable. Actually, I can actually show you what that looks like. I want the kernel image and the worker kernel image to be different. So let's do kernel. All that into .nvarc. nvarc. We'll use the line built. Equals. So with that environmental variable set, wow, I do my generate again. What happened there? Over time, add these to our environment variable set as well. Where's that external link again? Copy. All right, so now we have a new config, and it's pointing at the correct kernel. We're using their existing root file system. You think so? You're probably right, actually. You know what? I'll give you that one. That's probably true. I'm responding to Max. Max says that if you don't have list, then you can't do a get all. But if you do have list, you can only do a get by a specific name, which might be the problem, which might have actually been what was hanging me up. It's very possible. So we've got our cube config, or we got our quick start. Let's go ahead and apply it. F. Oh, good. J. Really provision. Split horizontally. M-A context. Printing. Oh, I'm seeing it. Seeing it scheduling though, that seems weird. Running. Wait for this guy to sync up again. All right. We have provisioned a node. I think that for this cluster, I can't remember, there was actually other stuff. All right. Nice. Well, so after that, now we can do this one, right? We can do cluster kettle. Hit kubeconfig, copy quick start. That we should see as a administrative kubeconfig for 1096. That is not going to work. Why would that have worked? Oh, you know what I got? Ah, all right. If we can delete it, kubekettle up, delete. Gotcha. I'll tell you why this is not going to work. This is not going to work because the cluster is sitting on the service IP of the inside of that cluster, and what I want is for it to actually be sitting on type load balancer. So let's take a look at that configuration again. We want machine count. We're going to set the worker machine count to like 3. So we'll break this real quick. Still present though. The delete didn't work, but we'll get there. So vim edit. Close 3. We want the service type to not be node port. Tink control plane service type equals load balancer. Service type. All right, so then Here. I'll get machines. Deleting. Oh, looks like we have a hang up on the finalizer. Get machine. Oh, create. Delete. Yeah, I think it's in there. So, delete context. Hyperlink. Delete. Start. Gone. I passed the finalizer so we can move forward. Machine. Clusters. So the finalizer, the machine finalizer, looks like maybe they're in their controller code isn't quite cleaning up correctly. I could have waited a little longer to see if it would actually end up doing it, but in an effort to move this forward, I just kind of cleaned it out. So apply again. Generate. C-N context. Load balancer was created. Machines-A W. And should be able to get this cluster up and running. Let's split our screen again. Kernel get machines, actually VM. W. Let's see, the control plane node is up. And there goes the worker nodes. Into scheduling. and into running. Cool. Cluster kettle to config. Quick start. You can see now that it's pointing out a service IP, that load balance IP. So I'm going to dump that into copy. For the worker nodes to register. That was a long way to go, but I think we're making pretty good progress. All right. There they are. This is going to be an acid test just to make sure Cilium installs, all the things work. And then we can check for BTF data, and then we can call it a day because I have to get to a doctor appointment at 1:30. So Vertink, pretty cool new hypervisor. Pretty neat that they actually have a cluster API implementation for it. Pretty neat that resource-wise, not too bad. 4-node cluster. Fully, virtualized enough anyway. Oh. Oh, image pull back off. What is happening there? I wonder if its DNS is broken or something. Let's do, let's see. Okay, it's root. Looks like we have another thing to fix, but let's see how far we can get here. It's probably not going to work because the image pull is not working. Nice. problem, I think, is that the nodes, the VMs, aren't getting DNS because it's almost always DNS. I don't think that let's take a look at the root file system that was created and see if it actually has a password, because if it does, maybe we can SSH in and see if I'm right about this. Image builder, rootfs, Docker file. I'm not seeing SSH get installed. Where's the makefile at? Makefile. This sudo password is password. Yeah. We're going to proceed with this in 2 weeks. I hope that you all found this pretty interesting. I know that it's kind of fun to watch other people kind of dig through problems that you've had in the past. And that's kind of where I'm at right now, as I'm in the process of trying to fix DNS on these guys, but I'm running out of time. And so we will revisit this in 2 weeks and continue with our efforts. But it's kind of a fun new cluster API implementation that is significantly less resources. So thank you all so much for your time. I hope you have a great weekend. I hope you're going to come see me in San Francisco next week. We're going to play with Liz like in live. So thank you so much. Have a great weekend. Goodbye.